Okay, so hi everyone. So today I'm going to talk about these two different approaches. One is the representative point selection, and the other is the simfluence. So they are both capable of doing this data attribution. And representative point selection is as you just mentioned, this is a classical method, whereas simfluence is a relatively new. I wouldn't call it an algorithm, but it's rather a general framework, which is capable of doing something more stronger than those traditional, say, inference-based attribution methods, which provide single scores to each sample. So let's get started. So representative point method. So before digging into the details, I think it will be useful for us to review because we have already covered many different data attribution methods in this reading group series. So I think it'll be useful for us to say at a high level to try to categorize them into different classes. So I think broadly speaking, from my perspective, I would categorize data attribution methods into two broad categories. So one is retraining-based algorithms, and the other is gradient-based algorithms. So retraining-based algorithms, so basically means that the algorithms typically involve training models on some subset of the training samples, and typically involve a lot of retraining. So this is why it gives rise to its name, retraining-based algorithms. And under retraining-based algorithms, so there are some very classical approaches, for example, the Shapley value, and also the more recently data models. Data models also involves training a lot of different models on subsets of the training samples. And the other line of work is called gradient-based approaches. So this line of work mostly it does not involve a lot of heavy retraining. So for instance, inference function and tracking. So a common characteristic of these algorithms is that they all involve some information of the gradient, either at the end of the optimization procedure, for instance, the inference function, or throughout the training trajectory, for instance, tracking. And today, we'll talk about another gradient-based approach, is representative point selection. So this also falls under this gradient-based framework. So representative point method. So at a high level, it relies on this representative theorem. So informally, this representative theorem says that the minimizer of a regularized functional over a reproducing kernel Hilbert space can be expressed as a linear combination of the kernel evaluations over the training samples. So this theorem seems to be a little mathematical heavy, but I try to make it as lightweight as possible. So generally speaking, you can just think of the problem that we are solving is some empirical risk minimization problem. Although here it is very crucial that we need to use some sort of regularization, for instance, L2 regularization. And this representative theorem essentially says that, okay, the minimizer of this regularized empirical risk minimization problem, it can somehow be expressed as some linear combinations of different linear combination of a lot of functions. And these different functions, they are native to each training samples. So as here, it says that the kernel evaluations over the training samples. So by doing this, essentially we can somehow express the final solution of this optimization problem to a linear combinations of functions which are intrinsic or native to each sample. So this is how representative point selections perform data attributions. So essentially, it is using this kind of representative theorem to break the final model into a combination of different components which are specific to each sample. So we can use a very simple linear model for us to gain some intuitions of how this representative point selection works. So say let's consider this regularized empirical risk minimization problem of a linear model. Say we try to find some zeta star that aims to minimize this objective function, which is 1 over n summation of this L zeta transpose xi. L is a loss function, and plus some L2 regularization term. So this is say we assume this L is say we assume L is a convex function, then this problem is essentially strongly convex and need a missing unique solution. So by solving this first order condition, we can see that this optimal parameter theta star, it can be expressed as a okay. The optimal parameter theta star can be expressed as a linear combination of the partial derivative of the loss function with respect to the parameter. And since this model we consider is a linear model, meaning that theta transpose xi is exactly the prediction that we use to produce. So this means that it's a linear model. So we can further.
One quick question. So
Mhm.
in the penalty term disappears somehow for the first order condition.
You mean the regularization term?
Yes.
No, actually, because the first order condition, you can see that. So actually, so in first order condition, for the L2 regularization term, you directly get a lambda theta, and then lambda theta plus some the gradient of the loss function with respect to the parameter equals to 0, and then you rearrange these terms, and then you get that theta star equals to the summation of the gradient.
Oh,
Yeah, so
okay.
this is how yeah.
Thanks.
Yeah, so this is exactly how representative point selection works at a high level. So you see that here it is very important for you to have this L2 regularization. This allows you to, because the gradient of the L2 regularization term is exactly the model parameter plus some scaling. So that's how you manage to do this kind of representative point method. Okay, so because this is a linear model, so essentially you can further simplify this expression, and then we get that the final expression. We see that essentially we can write the optimal model parameter theta star as a linear combination of different samples xi. So here, since different xi, it is just called the representative point in these very simple linear models, and then their corresponding coefficient, which is basically the partial derivative of the loss with respect to the model's prediction, and plus multiplied by some scaling terms. So this is called a representative value. So this representative value, you can just interpret it as how each sample contribute to the final model. So this is, at a high level, this is how we perform representative point selection. So okay, so but definitely we're not satisfied with just being able to perform this kind of representative point selection for linear models. So definitely we care about generalization to general nonlinear models, for instance, neural networks. So here, the setting that we consider is a classification task. And then the prediction model that we use will be the head y just equals to sigma plus composite with some phi, xi, and theta. So here sigma, so this is the sigma function. And then phi, this is the pre-activation prediction, and it can be further break down into two parts. So the first one is the linear head, which we call as theta 1. So it is of the dimension c and dimension c times m. And the second part is this feature extraction fi. So here we can write fi as another feature extractor. We just write it as phi2 xi plus xi and z2. So this is the feature that we use in the penultimate layer. So essentially the model parameters, we write it as a whole as theta, but essentially we can break it down into two parts. So one is theta 1 and the other is theta 2. So theta 1 just corresponds to a linear head, and theta 2 corresponds to the model parameter used in the highly nonlinear layers. So, and the objective function that we consider here is to solve the following optimization problem. We're still okay, so there should be a summation here, but the first part is just corresponds to the standard empirical risk minimization. But for the second part, so this is perhaps a little slightly different from what you might have expected. So intuitively, you will imagine that here, when doing this L2 regularization, we'll be doing regularization over the entire parameter, which is theta. But here, we kind of need to do it only on this linear head. We only regularize this theta 1. the norm of theta 1. And the reason is that essentially because we are trying to generalize from the previous analysis in the linear models to this general deep neural networks. And so essentially and if you still want to say try to break down the final models or the predictions of the final models into disjoint summation that corresponds to different data points, then essentially we need to ensure that we are still kind of using a linear model. But so if we consider using a general theta here, and then we consider the first order condition, then we should see that the gradient of the loss with respect to the model parameters will be very nasty, and this will not be good for us to obtain a similar formula as we did for the linear models. So this is very important here that we need to use the regularization only for the linear head rather than doing the regularization for the entire model parameters. Okay, so then after having this, then basically we can just repeat the analysis for the linear models, and then we can have this result for general neural networks. So basically say the theorem says that say X is a test sample and theta star is a stationary point of the regularized empirical risk minimization problem. So then we have the following decomposition of the pre-activation prediction. So recall that this phi is the prediction before the activation function, which is sigmoid. So we have the following decomposition. We can write phi as a summation of these different k, xc, xi, alpha I for I from 1 to n. So we can just interpret this each term to be native or intrinsic to each sample. So more specifically, we can have this formula for k, xc, xi, alpha I. So k, xc, xi, alpha I equals to alpha I fi transpose ft. And alpha I is defined as the partial derivative with respect to of the loss function with respect to the pre-activation prediction. So you see that this is pretty similar to the one that we have in the linear models, because in the linear models, the alpha I we have is essentially the partial derivative of the loss with respect to the prediction. But here we just slightly change it to from the prediction to the pre-activation prediction. So here there are a few comments. So first of all, here the representative value alpha I. So we still refer it to that representative value. But here, it is important to note that this alpha I is a c-dimensional vector rather than a scalar. So this is because that the dimension of phi is c. So basically because it is the pre-activation prediction, and we are focusing on this classification task. So we have c different classes in total. So this also means that this alpha I is a c-dimensional vector. And also the representative inference. So this is what we refer to as this k, xc, xi, alpha I. So we refer it to as the representative inference of each sample xi. We say that it's determined by both this representative value alpha I and as well as the feature similarity fi. So recall that this fi is just the penultimate layer feature for each sample. So it only concerns xi, but it does not really concern their labels. But in practice, when we are using this representative point selection to select some influential data point, we are the paper is only mostly using this alpha I for selection. So basically, sort of ignore this fi transpose ft when doing the selection, but they're only using this representative value. So because they think that this representative value is very, intrinsic to each sample and really characterize how each sample affects the final pre-activation prediction. So how do we actually use this alpha I, this representative value, to carry out some useful analysis or try to select some samples? So here I will describe the general procedure. So say we have a trend model that is obtained by minimizing, say, doing some empirical risk minimization process of regularization. And then we also have different samples, say from x1, y1 to xn, yn. So we can just use the previous formula to calculate these representative values for each I. For each I, the representative value alpha I is a C-dimensional vector. Okay, now say we have a test sample, let's call it xt. And for this xt, our trend model gives it a prediction. And say that our model predicts this sample as the J's class. You see that it gives a very high value for this J's class. So basically it means our model predict xt as the J's class. Then we will look at the J's column of these representative values. So this just corresponds to alpha 1j, alpha 2j, and then to alpha nj. So these are the values that we consider because we are trying to understand how each sample influence or contribute or negatively contribute to the model's prediction of this xt to be class J. So this is what we care about, mostly care about. Of course, we can also look at other columns, but they have different meanings, right? Because for instance, if you look at column 1, then we are basically interpreting as we're trying to understand how each sample corresponds, how each sample contribute to the models to make a prediction of 0.05 for xt to be the class 1. But I think the most interesting thing is that definitely we want to understand how the model, because eventually the model classify xt as the J's class. So this will be the column that will be most interesting. And after obtaining this column, the J's column of these representative values will be, there's some quantity of interest that we useful for our study. For instance, we can look at the absolute value of this absolute values of this column. So basically this absolute value just characterize how much the degree of contribution of each sample to the model's prediction on this J's class. We can also look at that sign. So the sign is also very interesting because here we can see that the sign actually means that whether this data point, it contributes positively or negatively to the prediction, for the prediction to be the J's class. For instance, if you observe a very negative value, then it actually means that, so this point actually try to prevent our model from predicting this data point as the J's class. On the other hand, if we observe a very positive value, then you will understand that, this point, so it is the main driving force for our model to eventually have this prediction of xt to be the J's class. So here we see that both the magnitude of these representative values as well as their sign, they can be useful for analysis. Okay, so now let's talk about how we actually do this implementation in, say, how do we actually, because the theorem involves some assumptions, so it's very important for us to understand how we actually do this implementation in practice. So there are two important considerations. So the first one is the L2 regularization, because we see that the whole analysis of this representative point selection, it relies on the use of regularization. Without the use of regularization, it basically means that there is no way that you can when you're using the first order condition, you basically cannot just obtain that formula, which is very desirable. So L2 regularization is clearly important. And the second point is that because in order to obtain such an equation that breaks the final model or the final prediction into a summation of different inference that is native to each sample, it is very crucial for us to ensure that we use the first order condition properly, meaning that we really need to ensure that the final parameter that we obtain is really a stationary point of the objective function that we use. So this is the two main important considerations that we need to take into account when we're actually optimizing a neural network. So say we can first discuss scenario one. Say how do we train interpretable neural network from scratch? So meaning that we just start from scratch. We want to train a neural network, and then we want to perform this representative point selection. So in order to do this L2 regularization, we can just use well-known results in the literature, which says that this L2 regularization is actually equivalent to doing weight decay. So yeah, this is not hard to prove. So basically, yeah, the objective function, the gradient of the L2 regularization, when you explicitly write it down, basically you can see that it is equivalent to performing weight decay. And weight decay is already incorporated in standard deep learning optimization libraries. So this problem is resolved. And for the second problem about the stationary point problem, the authors propose to continue fine-tuning the funnel layer, the linear layer theta one. Because if you do neural network optimization, then it's very likely that at the end of the optimization, you really do not reach a stationary point. Yeah, because you do not reach a stationary point to very high precision. So it is very important that here, after obtaining some neural network, which is of reasonably good quality, we need to continue fine-tuning the last linear layer theta one to ensure that we reach a stationary point to very good precision. So this is how the authors propose to meet these two criteria. The first one is to use weight decay, and the second one is to perform this continuous fine-tuning on the last layer. The second scenario I think is actually more interesting because in practice, the second scenario involves trying to interpreting a pre-trained neural networks. So it's very important to know that, for instance, in practice, say we are given a model parameter, the model parameter of a pre-trained neural network, but this model might not be trained using L2 regularization or weight decay. But in this case, we still want to perform this representative point selection. So yeah, and also we want to avoid doing retraining. So here the authors propose to perform fine-tuning using this teacher student objective. So basically so the original objective is that we will basically just optimize this try to match the pre-activation prediction, try to align this prediction with the samples labels. But here we're trying to actually match the labels, the soft labels that are actually produced by the teacher network. So the teacher network is exactly the pre-training network that we are given. So here, I think essentially this objective function is trying to balance two objectives. The first one is to mimic the original network. So by saying mimic the original network, this is very important because we want to make sure that the final neural network that we are trying to interpret is mostly the same, or in general, the behavior should be similar or the same to the original neural network. Otherwise, we will be essentially performing interpretation or representative point selection for a completely different neural network, right? Yeah. Otherwise, it might be as well that we just say retrain a model, completely do the first scenario, we just train a model using weight decay. So here, one important consideration is that we really want to mimic the original network. And the second point is that we need to additionally introduce this L2 regularization. And this L2 regularization just help us enable the representative point interpretation. So this is very important as well. Okay, so we have talked a lot about I think we have mostly finished. So what's this representative point selection, the technical details, and also the implementation. So we can now see some experimental results. So the setting the authors can consider is to fine-tune our pre-trained ResNet 50 on this AWA dataset, the animal with attributes. So the authors can perform multiple case studies, and we'll try to look at some of them, some interesting ones that I found. So here on the left column, is a test sample. So the neural network successfully do a successful prediction, predict as the grizzly bear. And here there are 6 columns on the right hand side. So for both represented point selection and inference function, here are the positive and negative top 3 samples that are selected. So basically, you can see that the first row, it just corresponds to the positive samples that are selected by represented point selection and inference function. And for the second row, it will be the negative samples selected by represented point selection and inference function. And here, the positive and negative just corresponds to what I described when analyzing or when trying to interpret the represented values. So basically, those with positive values, we just call them positive samples because they contribute positively to the final prediction. And for the negative values, we just call it negative examples because they are trying to hinder the model's prediction. So I think for this figure, it is pretty clear that both represented point selection and inference functions, they are capable of selecting meaningful examples. In the sense that for the positive samples, so they are basically just images of the same class and also predicted as the same class. And for the negative examples, we see that mostly they are just images that look very similar to bear. For instance, the label of the test image is grizzly bear. And we look at the first example selected by represented point selection inference function. I think it also looks like it is just a polar bear. So semantically, it looks very similar to the test example, but it actually has a different label. So I think it makes sense, right? And so these kind of examples will actually be harmful for the models to make the right prediction. So this intuitively makes sense. But here we can look at a different example. So here, the labels of the test example is a rhino. And we see here that for the represented point selection, I think it's still capable of selecting meaningful and expandable samples. So in the sense that the positive examples are still rhinos, and the negative examples are something that looks similar to rhinos but have different labels. But if you look at the examples selected by inference function, then you will see that I think most of them just does not really make sense. Yeah, right. Because I think both the positive and negative examples, they somehow both concerns ox or cow, which although they look similar to probably look similar to rhinos, but I just don't think that they really explain that why the models correctly make a prediction for rhinos. So I think based on these examples, we can make a conclusion that I think it's more robust in providing manifold examples, particularly in explaining why certain examples might be useful and why certain examples might be harmful compared to inference function, at least in this particular data set that the authors consider. Okay, so the second case study we consider is debugging data set. So we ask the following questions. What causes the model to make a wrong prediction? So there's some very intuitive answers to this question. For instance, data samples with wrong labels, and also as we just saw, semantically similar samples with different labels. So I think both of them are very intuitive answers to these questions. These are all possible explanations why models will make a wrong prediction. But the authors try to look very carefully do some case studies, and they actually identify a pretty less obvious pattern. So basically, we can see that the test sample here is it predicted as a deer, but the true label is antelope. And we saw, and the authors also for the right 4 columns, it just corresponds to the top 4. samples that are selected by the representative point selection. So we see that. So I think for figure 1, training ID. So the figures on the second column, the first column, and the last column. So if you look at these columns, then we see that actually there are multiple objects in these figures. So for instance, if you look at the figures in the column 2, we saw that actually they are both antelope as well as zebra. And for the fourth column, we saw that they are actually both antelope as well as elephant. So I think this is a very interesting observation. So, and it also reveals a less obvious pattern that for these images, these multi-label images, it can potentially confuse the model. So basically when the model, because these models these samples cause the model to somehow ignore the antelope in the figures, but somehow try to uh yeah, just introduce some noise to the final predictions. So multi-label images will confuse the
Yuzheng,
model.
I have
And
a quick question. So,
mhm.
like in this case, when you have a wrong prediction, so when you do the selection, do you use the column of the ground truth label or the column of the prediction?
Yeah, I think this is a very good question. So I think I don't think the authors include the details in this part, but I think both methods make sense. So I think in this case you can actually look at both columns, right? Because both are meaningful, because they just have different interpretations. If you look at the ground truth label, then you basically try to understand why our model didn't give very high values. We can try to find those instances that really prevent the models to give a high value to this ground truth label. And if you look at the labels that the labels that the neural networks actually predict, then it is also very interesting, right? Because we can try to find those samples that help to boost the model's prediction on this particular class. We can try to understand really what sample trying to really confuse the model to try to make a wrong prediction. So I think in this case, both approaches make sense. But I think the authors didn't report in details on whether they choose the first or the second approach. But based on my understanding, I think both approach make sense and they provide complementary understanding and explanation when trying to select samples. So I think this is another aspect of why this approach representative point selection is useful, because you can see that we can actually there are multiple different angles where we can try to understand why a model makes a certain prediction. And there are 3 classes we can look at. We can essentially just go beyond looking at the ground truth label or looking at the predictions that the model produce, right? So I think this is another aspect why this representative point selection could be useful.
Yeah, I think for this particular perspective, it is also true for influence function, right? So, I mean, you could use like a particular logic as the target
Yeah.
influence function. Yeah.
Yeah, that's true as well. But I guess my point is that, because for influence function, I guess you need to change the target function. But here, represent the point selection essentially because essentially you are trying to because you can compute all the representative values of I in the same time, right? So basically, the selection and the interpretation will be very straightforward and easy to implement.
Yeah.
So basically, you just do one computation. You don't need to really say change the target function and then redo the calculations.
Yeah.
Yeah. Okay. So I think this is the final case study. So this is concerns the saliency map. So this is also known as the sensitive map. I think this concept is very useful and frequently appear in the literature of explainability. Basically, just try to explain a model's prediction from the lens of certain pixels in a figure. So basically, it's a color map that highlights the pixels that are relevant for the prediction of a sample. So mathematically, it can be defined as the model's prediction, the partial derivative of the model's prediction with respect to the sample. So basically just I think it measures the sensitivity of the trained model's prediction to small changes in the input. So here a very important observation is that since we already have a decomposition of this pre-activation prediction, basically just we have for this representative point selection, we already decompose it into the summation of alpha I, the representative value, times Fi transpose Ft. So here we can just take the partial derivative with respect to the test sample. And then we have another decomposition formula. So basically, we just decompose the whole saliency map into a linear combination of the saliency map that that is native or intrinsic to each sample. This help us provide some more fine-grained explanations of how each sample, explains the final prediction of a model. So first of all, we look at the column on the left, the column on the left hand side. So this is a test image. The model predicted it as 0. And then if we look at the sensitive map or saliency map of this particular test image, then we see that so basically the bright area, it just corresponds to the most sensitive part. So for this particular figure, it means that the head region of this figure or the head of the zebra. So this is the most critical part for the models to make a prediction, meaning that if you slightly change the head area, the model will be likely to make a different prediction. And then for the 4 columns on the right, so they are basically just images selected by representative point selection. So we can first look at the right column. So here we see that this right column, this image, it has a very significant emphasis on the head of the zebra compared to the images on the middle. So basically, we see that similar to the first image. So this one also have a lot of emphasis on the head of the zebra, and correspondingly, when looking at the saliency map of this particular image, we see that it has very high overlap compared to the overall saliency map of the test image. So basically, the region is very similar to the one in the first figure, corresponding to the head of the image. Yeah, right. But if you look at other figures, for instance, the figures in the middle, for instance, we can look at the second column. Then we see that actually there are some the activated or the bright area in this figure actually correspond to the say the background of the image. So this basically means that these samples they contribute although they all have very high contributions to the model's final prediction, at least according to this representative value or the representative point selection, but they have different ways of contributing to it. The last image, it will mostly contribute to the model's prediction through the very significant head region. But for this image in the middle ones, actually you see that the background also contributes significantly, at least compared to the last figure. So basically, I think decomposing the saliency map, it just provide more fine-grained explanations on how each training samples contributes to the final prediction. So I think this is also pretty interesting. Okay, so let us do a summary of this representative point selection. So I'll mostly compare it to inference function because I think they are just for a very long time, representative point selection and inference function, there are 2 classical approaches in data attribution. So the strengths of representative point selection, I think one obvious one is that it has the computational efficiency is really it's very computationally efficient, particularly compared to inference function, because it just does not concern those very computational intensive part in inference function. For instance, the Hessian-Wetted product. And we see that the whole procedure and it's very simple, and it only involves computing the gradient of the loss with respect to the prediction, and this is also very computationally lightweight. So in general, if you do some calculations, do some complexity analysis, I think, generally speaking, I think representative point selection the computational step can be carried out in ON time, where n is the number of training samples. So this is very efficient compared to inference function. And also, as we have seen from these case stories, I think, although I wouldn't say that representative point selection is a better approach, and clearly it's not compared to inference function, but nevertheless, I think it provides complementary understandings. Yeah, for cases when inference functions fails or uh, has some drawbacks, I think potentially this representative point selection is capable of providing complementary understandings to this whole data attribution problem. And as for the weakness, I think they are also pretty obvious. The first one is their limited applicability. So basically, I think it is, I think, the assumption, although they can be implemented with some tricks, for instance, using weight decay and also using continual fine-tuning, I think it still are largely limited its applicability for expanding general deep neural networks. And also another limitation is that I think I'm not sure if this is clear in my presentation, but I think this general representative point selection for general deep neural networks is essentially a very trivial generalization of the representative point selection for linear models, because I think it does not really go beyond linear models in the sense that it's only expanding the training samples inference to the final linear layer. It does not really concern how its samples involves or affects the highly nonlinear part of the models, because it is essentially treating the nonlinear part of the part which involves the model parameters theta2 into F2. So for this part, I think this is not a concern, or this is actually not involved in the computation of representative point selection. So for those inference that are hidden in this nonlinear layers, so there is no way that representative point selection can expand them. So I think this is another very critical drawback or limitation of representative point selection. So I think based on my search, representative point selection for now has not been applied to large scale neural networks, for instance, to transformers diffusion models. Yeah, okay. So I think that's mostly for the first part, the representative point selection. So before moving to the second part, so are there any questions from the audience? Yeah, if not, I can move on to the second part. So the second paper that I'm going to introduce is called Simfluence. So Simfluence is actually, I think it's mentioned in the previous reading group, but here I think I will try to go a little bit more into the details. So Simfluence, so I think the motivation of this Simfluence is very simple. So basically it says that existing gradient-based data attribution methods, they fail to capture the non-additive interactions between samples. So for instance, we know that, for instance, if you inference function constantly under or overestimate group effects. So I think this is kind of, at least empirically, this is well known in the literature. And also, if you really focus on the training dynamics, doing some trajectory-based analysis, such as tracking, then another drawback of this approach is that they are unable to detect some nonlinear relationship between sample. For instance, redundancy examples, diminishing returns, etc. For instance, if you train a model using on data sample in a previous iteration, and then in a later iteration you train on the same sample, then the return or the gain that you obtain from these two iterations, they are clearly different. But this seems not to be modeled, yeah, in the previous existing analysis of existing data attribution methods. And I think this is actually I think this is actually an inherent weakness. So I think because for most of the existing gradient-based data attribution methods, I think a key to them is so-called this decoupling. So decoupling means that we assign a score to each sample, and I think this is the key to ensure that the scores are native to each samples. Otherwise, yeah, for instance, in influence function and in the representative point selection that we just described, so we need to really make sure that having a score to each sample, these scores are native to each sample. So mean that there couldn't be those interactions between samples. So this is actually an inherent weakness. So I think it's in general I think it's very hard to be overcome by any one pass procedure that is on a static score to each sample. So in this paper, the authors actually proposed not try to go beyond the previous solutions, but actually proposing not a solution, not an algorithm, but a general sequence-to-sequence framework. So the problem that the authors trying to solve is that given a curriculum, training curriculum, which is written as C, from C1 to C capital T. Well, capital T is just the number of training iterations. And here each CD stands for the training batch that used as step T. And we're also given an initial loss of a test sample. And here so here we're trying to produce a training run simulator that aims to simulate a loss sequence on the test sample. So basically, given this training curriculum and also the loss at the first step, we're trying to not only produce a static score, but rather produce a loss sequence for this particular training curriculum on this test sample. So intuitively, I think this offers much more richer information, much richer information compared to the previous approaches that assign a static score to each individual sample. Yeah, because here because you see that it's very flexible for us to say we can change we can remove a sample, and then correspondingly there are some changes in this curriculum. We can also change the order of the samples that are used in this curriculum, and then we can, by doing this, by being able to simulate the loss sequence, we are able to reason or argue counterfactually. So this is a very I think providing rich information is a very important advantage of this framework. And also intuitively there is an efficiency accuracy trade-off here, because actually if we just want to obtain this loss sequence, the simplest way forward to do it is just to train the model on this curriculum, right? Because if you train this model on this curriculum, then we directly obtain a very accurate the ground truth loss, the loss sequence, the ground truth. But there is naturally an efficiency accuracy trade-off here, because we want to avoid doing any of the training, because training is very efficient. So essentially we want the simulation to be very efficient, but we also want to maintain a reasonable degree of accuracy, meaning that although we are using less compute, the loss sequence that we produce using the simulator will be still reasonably good and reasonably close to the actual ground truths that we obtain using full training. So the simulator that the authors consider is that as follows. So given a test sample Z, each sample I is assigned a pair of learnable parameters AI and BI, and the change of loss is modeled as a linear Markov process. So basically, the loss at step T is only dependent on the loss at step T minus 1, and here the relationship between LTZ and LT minus 1Z is also very simple. So it's basically just a simple linear relationship. So it's just alpha CD times the loss at step T minus 1 plus some beta CD. And alpha CD here is the multiplicative coefficient. So CD is the corresponding batch size. So a natural way of doing it is just take the summation of these learnable parameters AI for those I that are in this particular batch. And similarly for the constant beta CD, this is the additive coefficient. So we'll just write it as the summation of these different BI. So this is a very, as I would say, this is a very simple model, but it still performs reasonably well. And learning the simulator essentially boils down to estimating these two vectors A and B, because once we have obtained this A and B, and also starting from L0C, which is the initial loss of this test sample, we can just recursively apply this linear relationship and then obtain the loss sequence. So this is how we obtain the loss sequence once we obtain this A and B. So learning the simulator essentially boils down to estimating these two vectors A and B. So how do we actually, what is the procedure that we use to estimate these two vectors A and B? So this is also, turns out that this is also fairly straightforward. So the first step is to collect some data. So we need to train the models multiple times in order to obtain multiple pairs of these consecutive pairs of loss, LTZ and LT-1Z. So this is very important. Now, we're not satisfied for only obtain the losses step t, because we are really concerning the relationship between the losses step t and the losses step t-1. So we are trying to, so when collecting the data, it's very essential that we collect these pairs of consecutive loss of data. So after having this collecting a lot of pairs of LTZ and LT-1Z, we can just minimize this regularized L2 loss. So basically, we're just trying to minimize LTZ and hat LTZ. This is our estimation. And hat LTZ, our estimation is just we just use the linear Markov process. So basically, we just write it as alpha CD times LT-1Z plus the additive factor beta CD. So actually you can see that, so because LTZ and LT-1Z, these are constant because these are the data that we use to collect. And the only thing that we really need to solve is this A and B, and also this AI and BI that are hidden in this alpha CD and beta CD. So essentially we see that, so this is actually a linear regression problem, a multivariate linear regression problem. So we can easily obtain these vectors A and B while the closed form solution of ridge regression. So this is essentially an L2 regularization linear regression. So the solution to this problem is actually easily solvable. There's no need to use any optimization. And we can also describe what is the connection of this approach to tracking. So this is the linear Markov process, which is called Simfluence linear. So this is the general formulation. But actually, there are two special cases that we can consider. The first one is that we just make the multiplicative factor. We just make it a constant, which is 1. So basically, we just only model the additive inference, but do not really model the multiplicative inference. The other way is the Simfluence multiplicative. So basically, we just make the additive factors a constant, which is 0. So we can see that we can check the Simfluence additive objective. So which is LTZ. If you just focus on, if you just ignore the multiplicative factor and make it 1, then the Simfluence additive objective is basically the square of losses. The square of LTZ minus LT-1Z minus BI. And also focus on, this is the case for batch size 1. Then the objective is just the square, the summation of the square. And the optimal solution to this Simfluence additive objective will be just a scalar times LT-1Z minus LTZ. For those iterations of batches that involve this particular sample, I. So we see from here we can see that this is actually the inference that is used in the tracking ideal objective. So this is how we this provides another way of interpreting this tracking ideal. So basically we can just interpret tracking ideal as a way of simulating this inference, but only using the additive factors and fix the multiplicative factors to be 1. So in other words, this tracking ideal can also be used to perform these simulations. Yeah, and for the other tracking variant, I think, which is the tracking checkpoint. So for that point, it involves using some first order approximation of the loss functions. So for that, I think it is also feasible to place in a similar framework, but instead we need to slightly change the loss here from the actual loss to their first order approximation. So, okay, so yeah, because the procedure is very simple, so now we'll just directly talk about experiments. So the goal is not really to, we first need to clarify what the goal is. So the goal is to really evaluate the simulator in the context of our fine-tuning. So it's not about fine-tuning, but rather try to see how our simulators perform are capable of predicting the loss sequence in the context of our fine-tuning. So the models we consider, the authors consider are T0 and T5. And the data set are just some standard NLP data set. One is RTE and the other is COPA. So the simulator that the authors consider are just Simfluence and their variants, because for Simfluence we also have 2 variants, because this is also for us to conduct some ablation studies to see whether, say, if you only consider the additive factors, or if you only consider the multiplicative factors, how it will affect the final performance of the simulators, and also the tracking variants. Yeah, so here I think, well, I think it's important to point out that I think tracking itself, or the variants themselves, they're not really capable of generating this loss sequence. I think it's only able to generate a loss sequence by interpreting tracking as a way of performing this additive Simfluence additive. So I think tracking itself is not used to, it cannot be used as a simulator. So it is only used as a simulator by building a connect. So you can build a simulator upon tracking, but actually tracking themselves, they are not really capable of generating the loss sequence. So the procedure is also, I think it's also very important to clarify, because we need to do trend validation and test bed, but here the trend validation test bed are not performing on the data angle, but rather it is performed on the simulation angle. So mean that we will run a lot of simulations. So some simulations are used for training. Some mean that when saying training, it means that they are used to collect those they're used to obtain the final simulator, meaning that we're using them to have an estimations of the 2 vectors A and B. And some simulations, we are using them to perform validation. So here validation is basically used for hyperparameter selection, because we're using L2 regularization to estimate the A and B. So here we need, for the coefficient of the L2 regularization, we need to use this validation data set, validation simulation. And finally, we need to evaluate the quality of our simulators on these test runs. So the trend validation test rate is very different from standard machine learning when we are performing on the data. Here we are actually performing this based on the simulation level. And the metrics that we consider, so 2 metrics. So one is the RCEP's MSE, the mean square error. So this is very simple, because we can use because we can train, say, given a curriculum, we can train the models to obtain the ground truth loss sequence. So we directly have the ground truth. So we can just compare our simulators performance. We can just relate it to the ground truth using the MSE. And we also concern the final steps, Spearman rule. So this is basically concerning, say, we have different data, we have different test samples. and how well our simulators are capable of predicting the ranking of the test sample at their final iterations. So here, because we only care about the rankings at the final iteration, so we only use this. So we only use the Spearman role coefficient, which is only sensitive to the ranking, but not the absolute value. Okay, so we have some quantitative results. So the method we consider here, we see that basically just tracking variance and also Simfluence linear, Simfluence multiplicative. And as we have explained just now, basically I think tracking ideal, you can just interpret it as Simfluence additive. So this is how we perform, how we use tracking ideal as a simulator. So this is basically the same as Simfluence additive. And so by looking at these tables, there are a few things to note. First of all, clearly that Simfluence linear. So this is the general method that take into account both the multiplicative and additive factors. So this performs the best. In the sense that it has the smallest mean square error, and also it have the highest Spearman stroke. So this is the first observation for both of these two data sets. And also there is another observation that by comparing Simfluence additive and Simfluence multiplicative, another observation is that none of these methods strictly dominates the other on all of these metrics. So this is also a very interesting observation, meaning that in some situations or for some tasks, modeling the additive influence turns out to be more important. But on the other hand, there are also circumstances when modeling the multiplicative influence to be more important. And taken together, it means that it is very crucial for the model to simultaneously model both the additive and multiplicative influence. So we also have some qualitative results. So basically just to give you some sense of how well the Simfluence framework actually perform in practice. So I think the blue one is the ground truth line, and the green one is obtained by the most powerful Simfluence linear. So yeah, I think especially for the first first figure, I think it's pretty I think it's pretty clear that I think Simfluence linear is performs surprisingly well in the sense that I think it's capable of predicting the spiky trajectory of individual sample losses with very high quality and fidelity. So I think it aligns really well with the ground truth. So I think if I'm really doing training and or trying to perform trying to anticipate, say, how well it will be by using this how the loss sequence will look like by using this particular curriculum. I would say that if I already have this Simfluence linear, at least from the first figure, I think it will be pretty strong in the sense I think it already captured the general trend and also some local fluctuations pretty well. So I think in this sense, Simfluence linear seems to be really powerful for this data, at least on this particular data set. Okay, so
So Yuzheng, I have a question regarding the experiment setup. So, like in this, when in this like training versus test, so there are different training runs, right? So,
yeah.
do they use the same curriculum or do they use different curriculum?
Yeah, so I think no. Of course I think they're using different curriculum, right? Yeah, because for instance in the training run, I think in order to collect different samples, you really need to use you need to have a lot of different samples. And by saying samples, I mean those pairs of consecutive losses on the test sample. So in order to collect these pairs of losses, you need to really run different. Curriculum in order to obtain a very diverse set a very diverse set of these pairs of consecutive losses. And I think in the training and in the testing phase, I think they're also using different curriculum. So I think training and testing, they must be using very different they must be using different curriculum. But one important thing to know is that, so at least for now, the framework that I described is only specific to one particular test sample. So this is very important. So meaning that if you really want to obtain a different simulator for a different sample, then it basically means that you really need to refit the values of A and B. So they're not so they cannot be reused. So this is a caveat. So this also makes the current framework less parameter efficient, which I will discuss shortly, because it basically means that for every sample you need to have these two and you need to estimate these two and two n parameters in order to simulate this in order to obtain such a simulator. So this is not really efficient, parameter efficient.
I see. I guess another question is like roughly how many training runs are required to?
Yeah. This is a good question. So I think we can have some intuitive understanding by looking at this linear regression problem, right? Yeah. So in this linear regression problem, we're trying to estimate because the number of model parameters we have. The number of parameters we want to estimate is 2n, 2 times n, because A and B, they're both n-dimensional vector. So intuitively, say if you just focus on this batch size of 1, then intuitively the number of training runs you need to the number of pairs of samples that you need to collect roughly on the order of ON. So in order to ensure that the solution is identifiable. So this is right. So intuitively, so this means that you can so this basically means that you roughly need to collect ON pairs of losses. And this can be and this also so this can be done in multiple fashions. First of all, you can either train a model for very long epochs, or you can train multiple models using different curriculums, right? So, but the whole point is to obtain some pairs of consecutive losses. So I think in practice, I think the authors they are doing the first they're doing in the first way. They're training multiple runs. If I recall correctly, I think for these particular experiments, the number of trainings that they use for each test sample is roughly 30. Yeah, 30 rounds.
Oh, okay.
Yeah.
Thanks.
So
can I have a question?
Yeah, sure.
Yeah, could you recap me like what is the reason that we are interested in to simulate this loss trajectory at the beginning?
Sure. So I think it's pretty powerful in the sense that so once we can use this figure to this figure to have some understanding, because I think it provides very rich information. Yeah, because basically it is a sequence to sequence model. You're given a curriculum, and then the simulator returns you loss sequences. For instance, if you want to understand at which epoch the loss decreases the most, meaning that the model is really learning a lot on this particular step, then what you need to do is just you check the loss sequence and identify the step which really gives you the largest job on the loss. And then you can also further locate the batch of samples that give rise to this largest job. And then you are able to reason that, okay, so at this particular iteration, because I'm using this batch of samples, the loss drops a lot. And then this is for a particular curriculum. And then you can also try to reason counterfactually. Say you can just remove a particular sample, right? Remove a particular sample from the curriculum, and then you try to see that whether it is still the case that at the previous iteration that gave rise to the largest job, is it still the case that after removing a sample, do we still observe the same job, or the loss, or the job, or the magnitude of the job decreases? And by doing this, you can actually, because if the simulation is sufficiently efficient, you can basically try to reason about anything, right? So by saying that after removing a sample, what will happen? Say after changing the curriculum, after changing the training order of the samples, what will happen? And I think basically there are a lot of stuff that you can reason about by looking at the loss on this particular sample. Although there are other objectives that can use, but at least for now, I think even by looking at the loss on a test sample, I think it already provides very rich information about the training dynamics and about how each sample or a batch of samples collectively affect the training precision. So I'm not sure, does this make sense to you?
Right. It make a lot of sense. Thank you. And I have another question. Like in the training procedure, right? You said we collected about ON, like trajectories for the training. Like it seems to me that the choice of the curriculum in the collecting could be very important, right? Because the curriculum can be their exponential possible curriculum. So how does the author, make this choice?
So I don't think the authors really I'm not sure. I didn't really check the details on how they choose the curriculum, but I guess the general, so I can describe some general principles when you try to from me, I think the choice of curriculum is actually not the most important thing for the of consideration here. I think the most important thing is that you cannot just choose two iterations just arbitrarily. For instance, if say the loss at step t and at step t minus 1, the loss on this test sample just doesn't change, because for instance at the end of the training you observe that the loss just didn't change, then I think this is basically useless, right? So I think you really want to collect those pairs of losses that contain rich information. So so this is the reason why they really need to run. They need to perform a lot of training rounds, but they cannot just because they cannot just say we perform one run and we train for say like infinitely long, because that still makes us that is still capable of collecting pairs of losses. But the problem is that at the end, when the model has already been trained to convergence, then basically the pairs of losses, and their relationship just doesn't give us a lot of information. So I think this is a very important consideration. So you will try to make sure that by using these particular samples and the loss and the consecutive pairs of losses, they really contain some information for us to reason about the coefficient. So I think this is a very important consideration.
Okay, so it's like as long as it's meaningful, right?
Yeah, as long as it's meaningful.
Okay, I see. Thank you.
Okay, so in summary, I've talked about this very general, this inference. I think it's a really general framework that is at least capable of, I think it's capable of simulating the loss sequences given a training curriculum. So I describe it as it is, but I actually, if you really think about it, I think I say it's general because actually it's capable of simulating algorithms, general algorithms that incrementally conceive training samples, and these actually, comprise much more broadly compared to what I described today, right? Because there are natural extensions to other metrics. For instance, here we consider the loss on a test sample, but it's not really need to be restricted to this particular metric. You can say consider other samples, for instance, the average loss on a couple of samples, a couple of test samples, and also you can concern how the norm of the parameters changes as training progresses. And also it naturally extends to all the learning paradigms in the sense that because I think it basically only requires that the algorithms is incrementally consuming training samples. So here we're talking about basically just supervised learning, but this is also true for all the many other popular learning paradigms. For instance, in reinforcement learning, the agents are basically just incrementally consuming the episode, right? So I think this framework is really useful. And also it is really a framework that goes beyond gradient-based attribution. Yeah, so, and I wouldn't say that this is naturally is more efficient compared to those gradient-based attribution. And I think often the case it is not, because it also involves a lot of retraining. But I think because it does not really depend on the gradient, and it's basically just trying to use a lot of information that you use that you obtain by running different simulations, by performing different rounds of training. But so it actually avoids some problems that are intrinsic to gradient-based attribution. For instance, those storage issues, those memory issues that you frequently encounter, say in those gradient-based attributions, say in inference function. So there are a lot of benefits for this framework because does not really rely on those gradient or Hessian information. So from my perspective, I think so this framework is essentially using more information from training, in the sense that because for those previous attribution methods, so most of them does not really use a lot of information. For instance, for inference function, it basically just rely on the final checkpoint of the model. And for track in, so it's basically just using a single run. So here, I think the authors claim that or observe that actually in practice, model developers often say model developers not usually it is the case that they perform multiple rounds of training before finally obtain a model that is desirable according to some metric. So it is often the case that we have more information beyond the single model checkpoint or a single run of model training. And I think the author's claim is that by leveraging this information, so we can have much richer information of how each sample affects the overall training procedure. So there are also some limitations of this work. So one thing that I just talked about is the parameter efficiency, but I think this is not really a problem, and it can be easily addressed by, say, using some encoders parameterized by neural networks. Say for the multiplicative and additive coefficient, we can use it in the current form in the form in this way. But also, I think this also raises some other issues. For instance, when you are trying to optimizing a new, because the current bottleneck of this inference mostly comes from you need to perform a lot of trainings. You need to perform multiple runs in order to collect those samples. So this main bottleneck lies in the data collection step. But for the estimation step, because it is a linear model, so it's very, very efficient for you you can actually just directly, after obtaining those data, you can just directly get what A and B is. But if you try to make this more complicated or more sophisticated, then it also gives rise to other problems. For instance, how whether it requires more data for you to train a neural network, and whether there is a potential chance of overfitting. So these are some very important considerations when, say, using these feature encoders using neural networks and going beyond the current linear models. Beyond the current linear models are using the current paper. So and also the linear macro process, I think it is still so this is also another limitation, right? Because linear macro process basically just model the loss at step t as a function at t-1. Macro process basically means that the path process the past data and the past numbers, they're basically just irrelevant. But this is usually not the case. Yeah, right. For instance, it is likely that there's some supermodular interactions between samples. For instance, at step 1, I learned that A belongs to B, and at step 2, I learned that B belongs to C. So it's only possible for you to learn that A belongs to C when you are combining these two steps together. So this is really amazing in the current linear Markov assumption. And finally, I think, yeah, I'm not really sure about this, and I'm actually pretty surprised that the authors didn't really discuss this in the paper. Is that I think the randomness in training is not really carefully modeled in the current paper, in the sense that, yeah, it seems that the authors assume that, yeah, say when you have a training curriculum, and then you have a starting point, it seems that, and then you just perform training, and then you sort of have the ground truth. But I don't think that this is really the case, right? I think there's some inherent randomness in training, and I think it's very likely that, say, you have, ignoring the context, very broadly speaking, if you train a model just due to this, just due to the randomness, actually, yeah, yeah, actually, I think, probably this is not a problem, because I think because if you start from the same initialization and then you fix the curriculum, then I think, then I think there is no randomness in training. Yeah, I'm not sure if this is the case. Yeah, I'm probably being wrong in this item. Yeah. Yeah. Yeah, in any case, I think that's mostly my presentation. So if there's any questions from the audience, I'm very happy to answer.